No. Uh, Last time we looked at planetary motion, and what we did was we showed that from Newton's understanding of the inverse square law, we derived two of Kepler's laws. We derived the idea that, first of all, that Kepler's first law, this is now in first law, planets travel in ellipses. The sun at the focus. We also derived the second law, which was at Kepler's second law. Said that a planet sweeps out equal areas in equal times. And if you remember what that meant was that here's the ellipse, here's the sun at the focus, and so if we keep going at equal time, so if that's t equals 0, t equals t naught, t equals 2 t naught, t equals 3 t naught, t equals 4 t naught, etc., then these are all equal areas. The third law. Well, the third law is a relationship between a planet's year, i.e., the time it takes from going all the way, making one orbit, and the what's called the semi-major axis. And as you'll see, what we're going to do is we're going to look at the relationship. If we've got an ellipse, what do I mean by a semi-major axis? Well, okay, so there's several properties of the ellipse you need to know. So if I've got the focus there, the semi-major axis is this. It's usually called A. And this is the semi-minor axis, which is usually called B. And if you know anything about ellipses, ellipses have the formula x squared over a squared plus y squared over b squared equals 1. That's a Cartesian equation for it. Now, what we've already seen that if I have my little planet and sun's at the focus, and that's the distance r to my planet. So there's my sun, there's my planet P, and this distance we'll call r. We saw from last time that r has the form 1 over p minus q cos theta. And so where are we measuring the theta from? We're measuring theta this way. That's theta there. So what's the point of this? Well, we determined that the area is given by the integral of half r squared d theta. And so if we want to go the area of the ellipse, and that's from 0 to 2 pi. And then if you remember, what we can do is you can use the chain rule here and do a bit of transformation into time t. So one period, so that's going to be, so t is going to be the length of the year. And you see, if I do it this way, make a change of variable, like that, which is quite nice. Then you remember from last time that this quantity here is the angular momentum. That situation, we know that's constant. That's from 0 to t of, and we called it mu, if you remember. That's mu dt, and that's a really easy integral to calculate, even when I make a typo like that. So look, there it is. So the area of the orbit is given by the angular momentum times the, the, the time period, the year, divided by 2. That's not all, because you see, the point is we know area of ellipse. One of these days I must learn to write properly. Area of an ellipse is equal to pi a b. So that, remember, that's your semi-minor axis and semi-major minor axis and major axis. So what we know is that mu t over 2 is equal to pi a b. And so essentially our task now is just to work out what the semi-major and semi-minor axes are. To do that, there are lots of different ways. I'm going to try and do this purely algebraically, i.e. without using calculus. You can use calculus to do it, but I think it's nicer if we just use pure and simple geometry. In this case, Cartesian geometry. What we want to do is, if we know that r is equal to p minus q cos theta, and x squared over a squared plus y squared over b squared equals 1 are the same ellipse, the task now becomes find a and b in terms of p and q. That's our task. Actually, it's not too bad. Okay, so first of all, we need to know, here's our triangle, there's the sun, there's the planet, there's theta, there's r, and we know that this is x and this is y. Now we've got slight difficulty here, slight geometric difficulty in that the distance x is not from the center of the ellipse, it's from one of the foci. And so what we're going to expect to happen is we'll need to change our coordinate a little bit, just to move the ellipse over, so that we can find out what the semi-major axis and semi-minor axis are. That's not going to be too much of a problem. It's going to be a question of working with quadratics. So what we do is this. We say, first of all, x is simple trigonometry, x equals r cos theta. So that's the same thing as saying cos theta, and r is p minus q cos theta. Oops. So do a little bit of work, we get xp minus xq cos theta equals r is equal to cos theta. So I'm clearing the denominator here. Move things over to one side. xp is equal to xq cos theta plus cos theta. So we can say that that's just simply xq plus 1 times cos theta. And now we have cos theta in terms of x, p, and q. we know that y, that's a good thing to know. The only thing to know is that y equals our sine theta, which is sine theta over p minus q cos theta. So it is same sort of thing. So yp minus yq cos theta equals sine theta. Right, now what we have now is we've got our formula for cos theta above, and that tells me that sine theta is equal to y q times xp over 1 plus xp, xq rather. Sorry, better make sure I don't mix my p's and q's. Put my p's and q's here. Okay, so now to simplify that out, and we have that all over one denominator, yp plus yp xq minus yqxp over 1 plus xq, and you notice there's a nice bit of cancelling there, yp over 1 plus xq, and that gives me sine theta. That's rather lovely. Because you see now what have I got? I've got from here, I've got this. Oops, don't do that. I need to do my technology a little bit better, don't I? So take that, copy that. So now we can put those together. There they are, together at last. We've got these two things, and we now know we can use the Pythagorean identity. Really nice thing. So basically we're going to do 1 equals cos squared theta plus sine squared theta. We know that, the old, good old Pythagoras. And that's, so we know that's, well, that is, get this right, xp over 1 plus xq squared plus yp over 1 plus xq squared. What's nice to notice here is that we have the factor p squared over 1 plus xq squared, oops, coming out, x squared plus y squared, which is rather nice. And then bring that over, so we've got 1 plus xq squared is equal to p squared x squared plus p squared y squared. And that needs a little bit more unpacking. 1 plus 2 xq plus x squared q squared equals p squared x squared plus p squared y squared. And we're going to do what I said we'd have to do. We notice that we've not got things in the nicest possible way. And that's because our ellipse isn't centered at the at its center. It's centered at the origin. It's centered at the focus. So we are going to get this. We can deal with that. Minus 2xq plus p squared y squared, and then so that's p squared minus q squared x squared minus 2xq plus p squared y squared. Now what I'm going to do is, as I say, this bit here is, as I say, it's because our coordinate system is centered at the focus of the ellipse and not at the center of the ellipse. So what I'm simply going to do is I'm going to complete the square. How do I do that? Well, first of all, I'm going to do it slightly long-winded way. I'm going to do it. Take this outside here, p squared minus q squared into x squared minus 2q p squared minus q squared times x plus p squared y squared. That stays. We can really nicely. That's actually quite a nice square to complete because you can see you can see that it's x squared minus twice something times x. So we just need the something squared to add in to give me the perfect square. So so what I've got to do is what's the something? The something is it's something is q over p squared minus q squared. So I'm going to square that and add it in. But of course, that which I add in, I must take away again in order to preserve equality. And I've still got the p squared y squared. Now this is where it goes a little bit more. So I've still got the p squared q squared. This here, this is my perfect square. That is x minus the something, which is p, which is q over p squared minus q squared. So that's that bit, and we've still got our q squared over p squared minus q squared, all squared, and we've still got our little y element here. Okay, so what I'm going to do is going to do a little change of coordinates, and as I say, what I'm going to do is very simple. I'm just going to put x twiddle equal to x minus, what's it now? Where's it gone? There, q over p squared minus q squared. If I do that, then I've still got my left-hand side being 1. 1 is equal to p squared minus q squared times my x twiddle squared. So now it's nice and centered. Minus q squared over p squared minus q squared all squared plus p squared y squared. Now do expansion. P squared q minus q squared minus q squared over p squared minus q squared plus p squared minus y squared. Okay, bring the constant term over, so we have 1 plus q squared over p squared minus q squared equals, now we're getting very near to the Cartesian form of our ellipse. Let's just sort this bit out first. That's quite nice, because what have I got? I've got p squared minus q squared over p squared minus q squared plus q squared over p squared minus q squared equals p squared minus q squared plus p squared y squared. Oh, and look at that. Look what happens. The denominator simplifies magically to this. Divided by the left-hand side gives me this. And then, now we know, because what have we got? We've got to have 1 equals, in this case, because we're centering at the origin, x over a squared plus y squared over b squared. And so now we know that A is going to be equal to P over P squared minus Q squared, and B is equal to 1 over, quickly look at that again, 1 over the square root of that. And it's quite interesting that what's that? That is the same thing as this. So basically, this is the square root of P to the A to the half. That's B. And so what do we know? We now know that the area of the ellipse is equal to pi A B. But now look, we've got here, so what we've just essentially said is that this thing is pi times A times root P A to the half, which is equal to pi over root P of A to the 3 over 2. And that, we have said, is this. So, still got this annoying half here. What I'm going to do is this, so square both sides. Mu squared T squared over 4 equals pi squared over P times A cubed. And that, believe it or not, is Kepler's third law. And Kepler states it like this, that T squared is directly proportional to A cubed. So the square of the year is directly proportional to the cube of the semi-major axis of the planetary motion. And if you now go through and look at your data for planets, if you're told what the semi-major axis is, work it out in terms of astronomical unit, which is basically divide the planet's semi-major axis by the Earth's semi-major axis. And that'll give you the distance in what are called astronomical units. Cube that, take the square root, and that should give you the orbit of the planet in years. So I'm going to leave you to try that because it's quite fun. But that's where we are. That's Kepler's third law. Orbital geometry. No calculus there for once. Thank you for listening to me. I hope you have a really good day. See you soon.